This session is about theoretical analysis of algorithms. In theoretical analysis, it uses a high-level description of the algorithm instead of an implementation. So here we do not have an implementation, we have a high-level description. Here we characterizes running time as a function of input size. So all the possible inputs are considered. So it does not mean that we input all the numbers, but it's a high level description of the algorithm. And let's see how we're doing it. It allows us to evaluate the speed of an algorithm independent of the software hardware environment. And it's done using the pseudocode. So as I mentioned, it's a high level description of the algorithm. So it's a high level description of the algorithm instead of an implementation. So in this example, calculate partial sum. So we have a function in sum which takes parameter. First we have int partial sum. Next, partial sum equals 0. Then we have a for loop, and we have inside the for loop partial sum plus equal I into I into I. Few operations and the return statement. So here, by inspecting the pseudocode, we can determine the maximum number of primitive operations executed by an algorithm. So we take it as a function of input size. And here we inspect the pseudocode and determine the maximum number of primitive operations executed by an algorithm. So we have 4 lines here. Partial sum equals 0, 1. For loop, another line. Partial sum plus equal I into I into I, another line. And the return statement, another line. So if we consider those 4 lines, line 1 and line 4 count for 1 unit each. The assigning and the return 1 unit each. So we have it like that. Then line 3, it is inside the for loop which executes n times, each time 4 units. So we have 4 units. Since it is executed 4 times, we have 4 units. So partial sum equals 0, 1 unit. Return statement, the last statement, 1 unit. And the third statement, line 3, it executes n times and there are 4 units. So it's 4n. And line 2, finally we are looking at line 2, and 1 for initialization, n plus 1 for all the tests, and n for all the increments. In the for loop, so initialization happens only once, so 1 for initialization, and the checking the condition I greater than, I less than or equal, or I greater than or equal, any sign like that. So here in this example, the condition part in any for loop executes m number of 1 times. The final so the I is gradually incremented, and if I doesn't match with the condition, it goes outside the loop. It will not go on inside the loop, but that count is taken. Therefore the condition is checked n plus 1 times. Since the condition is checked n plus 1 times, so we have n plus 1 for all the tests and n for all the increments. The increment will happen n times. If you carefully analyze the for loop, you can see the initialization will happen once, checking the condition will happen n plus 1 times, and increment I plus plus will happen n times. Therefore total is 2n plus 2. So if we add these things together, we get 6n plus 4. So let's talk about these primitive operations. So those are basic computations performed by an algorithm, identifiable in pseudocode, largely independent from the programming language, exact definition not important, assumed to take a constant amount of time in the RAM model. So examples: evaluating an expression, assigning a value to a variable, indexing into an array, calling a method, returning from a method. So if we look at this example again, we have a function to calculate the cost. Line 1 and line 4 for 1 unit. Partial sum equals 0, and the return statement 1 unit each. Line 3 executed n times, which is inside the for loop, so it is 4n. And next the line with the 4, and we have line 2, that is 1 for initialization. So for initialization we have 1, n plus 1 for all the tests. The condition is checked n plus 1 times, n for all the increments, therefore it's 2n plus 2. For initialization we have 1, n plus 1 for all the tests, n for all the increments, we have total n plus 2n plus 2, and altogether 6n plus 4. Primitive operations. So let's see the asymptotic analysis of algorithms. Here it's an analysis of an algorithm which determines the running time in big O notation. To perform such analysis, we find the worst case number of primitive operations executed as a function of the input size. We express this function with big O notation. Example: we determine the algorithm partial sum executes at most 6n plus 4 primitive operations. So when we have 6n plus 4, we say that algorithm partial sum runs in O(n) time. So the reason is, since the constant factors and lower order terms are eventually dropped anyhow, we can disregard them when counting primitive operations. So when we are considering about the primitive operations, we can disregard the constant factors and lower order terms. So if we have 6n plus 4, we can disregard the constants, so it has n. Therefore we say that the algorithm partial sum runs in O(n) time. algorithm partial sum runs in on time. The rule is, in asymptotic algorithm analysis, since the constant factors and lower order terms are eventually dropped, we can disregard them when counting primitive operations. So we disregard constant factors and lower order terms. So here's an example of big O notation. To simplify the running time estimation for a function fn, we ignore the constants and lower order terms. So we ignore the lower order terms and constants. So in this example, 10n cubed plus 4n squared minus 4n plus 5 is on cube. We ignore the constants and lower order terms. So here we discussed about theoretical analysis, which uses high level description of the algorithm. So it's done with pseudocode. An example we discussed to calculate the cost. So next we looked into primitive operations. Next, the asymptotic algorithm analysis. There we ignore the constant factors and lower order terms. So previously we got the cost as 6n plus 4. So once we ignore them, we ignore the constant factors and lower order terms, we get on time. So next we looked into an example of big O notation. Here we ignore the constants and lower order terms. That's the end of the session.